In the last lesson, we saw that when we took the natural log of both sides of a particularly difficult function, we could use the properties of logarithm to break it up into a whole bunch of little pieces and then kind of pick them off one at a time, take the derivative. It was a lot easier. And that's actually a whole strategy. It's a whole type of differentiation called logarithmic differentiation. So let's take a look at that. I'm going to give you some rules for it, and then we'll look at 3 examples. All right, so logarithmic differentiation. The idea here is we've got some big, nasty, ugly function, and we want to break it up so we can take the derivative of it. So the first thing we're going to do is we're going to take the natural log of both sides. Now, if the equation is equal to y equals something, then we know we're going to have the natural log of y, and we know the derivative of that. And then we're going to use the properties of logarithms to expand, to simplify, to break it all up into a whole bunch of different pieces. This is something we've been doing since Algebra 2, although we never talked about why are we doing it. Well, here's why. This is the whole reason. Because we've got a function that's very difficult, we can break it up and make it a lot easier to deal with. So once we've broken it up using the properties of logarithms to expand it, now we want to differentiate implicitly with respect to x. Because we're going to have the y on one side, the natural log of y, we're going to have to deal with that, and we'll have our y primes, or our dy dx's. And then finally, we want to solve for dy dx, or y prime. In these examples, I'm getting sick and tired of writing dy dx, so instead of dy dx, I'm going to write y prime. Remember, these are the same thing. These are the same thing. All right, so let's take a look at 3 examples of this. In my first example, I'm going to have y equals the natural log. Nope. I don't want to do that one first. In my first example, I'm going to have y equals x to the power of x. There we go. Let's do that one. This is one that I've seen on the AP. I've heard about this one on the AP. So, step 1, take the natural log of both sides. The natural log of y equals the natural log of x to the power of x. Now I'm going to use properties of logarithms to simplify it. Natural log of y equals x times the natural log of x. Now I'm going to differentiate. I'm going to take the derivative of both sides. When I take the derivative here, so I'm going to take the derivative of the natural log of y equals x times the natural log of x. When I take the derivative of the natural log of y, I'm going to get 1 over y dy dx, which I'm writing as y prime now. Dy dx, y prime, it's the same thing, equals, okay, what's happening over here? Over here I've got product rule, x times the natural log of x. So it's going to be the first times the derivative of the second plus the second times the derivative of the first. So simplifying it here, I'm going to get y, 1 over y times y prime is 1 plus the natural log of x. Multiply both sides by y. Y prime is y times 1 plus the natural log of x. Here's where we need to do our substitution. Oh, it's off the screen. There we go. What is y really? Y is x to the x. So I'm going to substitute that in here, and I get that my derivative is x to the x times 1 plus the natural log of x. And I could multiply that out and clean it up here a little bit and get a final answer of y equals x to the x plus x to the x natural log of x. For y equals x to the x. All right, let's take a look at another example. This one's a difficult, an awkward one. This one's going to be a tough one here. Y equals, and I'm going to have 10x cubed over the square root of x plus 1, the whole thing to the fourth power. So you can see this is just very difficult function to try to take the derivative of. I can see that I've got an outside and inside something to the fourth power, 4 times this, times the derivative of this, and then I've got quotient rule and I've got a chain. I've got a chain within the quotient within the chain. So could I do this using all the other methods? Yes, absolutely. But I think this would be a little bit easier if we did it with logarithmic differentiation. So in logarithmic differentiation, the first thing I'm going to do is take the natural log of both sides. And I get the natural log of y equals the natural log of 10x to the third over the square root of x plus 1 to the fourth. And now I'm going to use the properties of logarithms. I know in a minute I'm going to differentiate this, and the derivative of the natural log of y is going to be 1 over y times y prime. And then I'm going to multiply both sides by y, and I'm going to stick that in there. I know this is all coming. But I'm going to break this up. So I'm going to have the natural log of y equals 4 times the natural log of 10x to the third over the square root of x plus 1. Continue to break this up. 4 times the natural log of 10x to the third minus, don't forget that 4 times the natural log of x plus 1 to the 1/2 power, the square root, quotient rule of logarithms. Break this up. I'm going to have 4 times the natural log of 10 plus 4 times the natural log of x cubed minus 1/2 of 4 is 2 times the natural log of x plus 1. Look at all this properties here. All of this that we've been doing for years, breaking up logarithms, all of a sudden really has a purpose. I think I can do one more simplifying here. So I'm going to have 4 times the natural log of 10. Now that's just going to be a constant, isn't it? When I do the derivative of that, that's going to disappear. Plus 12 times the natural log of x minus 2 times the natural log of x plus 1. So breaking it all up into a whole bunch of different logarithms here. And now I think we're going to be able to do these, almost in our head at this point. Don't forget we've got the natural log of y here. So now I'm going to take the derivative of both sides. I'm going to take the derivative of this whole thing. All right, when I take the derivative of the natural log of y is going to be 1 over y prime equals the derivative of 4 times the natural log, that's a constant. The derivative of a constant is 0. Plus 12 times the derivative of the natural log of x is 1 over x minus 2 times the derivative of the natural log of x plus 1 is 1 over x plus 1 times the derivative of x, which would be just times 1. So 1 over y times y prime equals 12 over x minus 2 over x plus 1. Now let's solve for y prime. Multiply both sides by y. Y prime is going to be y times 12 over x minus 2 over x plus 1. And what is y? From the original equation, the original problem, there is my y. Substitute that in here. Y prime is 10x to the third over the square root of x plus 1 to the fourth power times 12 over x minus 2 over x plus 1. And I think that's how I would leave it. Don't do any simplifying. I'm not going to get common denominators here and simplify them. I'm not going to do any of that. Don't want to get hung up on the algebra. This is going to be my final answer. This is the derivative of that function right there. Yeah, I told you it was a kind of tough one. All right, so let's look at one more, the one that I started to do a little bit earlier, and then I said, nope, I wanted to change it. So let's look at that one now. And that one was y equals the natural log of the square root of x squared plus 1 over 2x cubed. And of course, we're going to have a restriction here that x is going to have to be bigger than 0. So if I take the derivative of this, now it's already got the natural log here. So if I take y prime, it's already got the natural log. I'm going to use this to break this function up into a whole bunch of little pieces and then take the derivative of each piece. So using properties of logarithms, I'm going to get y equals the natural log of x squared plus 1 over 2x cubed to the 1/2 power, 1/2 times the natural log of x squared plus 1 over 2x cubed, 1/2 the natural log of x squared plus 1 minus, don't forget the 1/2, times the natural log of 2x cubed. I can break this up some more. Can I break this up right here, x squared plus 1? No. So 1/2 the natural log of x squared plus 1 minus 1/2 the natural log of 2 minus 1/2 the natural log of x cubed. One more simplifying right here, and then we'll do the derivative. 1/2 the natural log of x squared plus 1 minus 1/2 the natural log of 2. This is a constant, right? Natural log of 2, 1/2 of that. I'm going to be able to, that when I take the derivative, that's just going to disappear. Minus 3/2 the natural log of x. All right, now I think I'm ready to do the derivative here. And we've broken it up to the point where we can do the derivative in our head. So, whoops, that shouldn't be a y prime yet. It should be a y prime here. That should not be a y prime. Now, the 1/2. What's the derivative of the natural log of x squared plus 1? It's going to be 1 over x squared plus 1 times the derivative 2x. Minus nothing. The derivative of a constant is nothing. Minus 3/2. What's the natural derivative of natural log of x? 1 over x times the derivative, which would be 1. Let's simplify this, clean it up here a little bit. My y prime is going to be, I can see that the 2's are going to cancel here. I'm going to have x over x squared plus 1 minus 3 over 2x. All right, there it is. So that was a tough one. Let's do one more. Bonus problem. Got plenty of time on the video. One more. See if you can stay ahead of me on this one. Suppose I give you the function y equals 10x cubed over the square root of x plus 1, and the whole thing is to the 4th power. So looking at this, I can see that I've got a chain rule here. I've got the outside function is u to the 4th. The inside function is this. The derivative of this is going to be quotient rule. And in here, I've got a chain. I've got a chain inside the quotient, inside the chain. And certainly we could do it that way and get one nice long answer here. But this is a great candidate for logarithmic differentiation. So I'm going to take the natural log of both sides. The natural log of y equals the natural log of 10x to the 3rd over the square root of x plus 1, the whole thing to the 4th power. And now using the properties of logarithm, I want to break that up into a whole bunch of different things. And we'll get to the point where we will be able to do it, all the different pieces, in our head. All right, the natural log of y equals 4 times the natural log of 10x cubed over the square root of x plus 1. The natural log of y equals 4 times the natural log of 10x cubed minus 4, don't forget that 4, the natural log of, and I'm going to write the square root of x plus 1 as x plus 1 to the 1/2 power. Let's break this up. Natural log of y equals 4 times the natural log of 10 plus 4 times the natural log of x cubed minus 2 times the natural log of x plus 1. I think I can do one more simplifying here, and then we'll take the derivative. Natural log of y equals 4 times the natural log of 10, there's our constant, that's going to disappear, plus 12 times the natural log of x minus 2 times the natural log of x plus 1. So now take a look at this. After we've broken it up, this is very difficult, very confusing. There's a lot of stuff going on here. Now take a look at this. I mean, I can do this in my head. I know that's going to be 0, 12 times 1 over x, minus 2 times 1 over x plus 1 times 1. All right, so let's do the derivative. And of course, there's always that one issue left. What are we going to get over here when we do the derivative? When we take the derivative, I'm going to have 1 over y times y prime, the dy dx. So I know I'm going to multiply by y, the original function here. The derivative of this is 0 plus 12 times 1 over x minus 2 times 1 over x plus 1 times 1. So 1 over y times y prime equals 12 over x minus 2 over x plus 1. Look how simple this has become. Multiply both sides by y. Y prime is going to be y times 12 over x minus 2 over x plus 1. But what was my y in my original function? So looking back in my original function, it was 10x cubed over the square root of x plus 1, and the whole thing was to the 4th power, times 12 over x minus 2 over x plus 1. And there it is. There is my derivative. All right, well, take a look at it. What do you think as we're doing this? And the more you practice, just like any other skill, the more you practice, the easier that it should get. All right, ladies and gentlemen, good luck, and I will see you for the next lesson, related rates, and it's going to get a little tougher with related rates.